Introduction to ISA. The instruction set architecture is a protocol that defines how a computing machine appears to a machine language programmer or compiler. The ISA describes the memory model, instruction format, type and modes, and operand register types and data addressing. Instruction type includes arithmetic, logical, data transfer, and flow control. Instruction modes include kernel and user instructions. What is machine language? Machine language is the lowest level programming language, except for computers, that utilize programmable microcode. Machine languages are the only languages understood by computers. In machine language, registers store collection of bits. All data and instructions must be encoded as collections of bits. Bits are represented as electrical charges. Control logic and arithmetic operations are implemented as circuits which are driven by the movement of electrical charges. So, the instructions directly manipulate the underlying hardware. The collection of all valid binary instructions is known as the machine language. The diagram shows layer of abstractions. Above ISA is concerned with how to program a problem, and below ISA is concerned with what needs to be built to make it run fast with lower power. An abstract machine, also called an abstract computer, is a theoretical model of computer hardware or software system used in automata theory. Abstraction of computing process is used in both computer science and computer engineering disciplines and usually assumes a discrete time paradigm. ISA is the language of machine. It is primitive compared to HLL and easily interpreted by hardware. Instruction set design maximize performance, minimize cost, and reduce design time. MIPS is an example of instruction set. It is real and simple to understand. Used by Sony PlayStation, Silicon Graphics, NEC.
MIPS, instruction set architecture or machine language. They are very simple instructions, all 32 bits wide, very structured with no unnecessary baggage. There are three instruction formats in MIPS: R, I, and J. Basic arithmetical logical instructions are R format, while load, store, and conditional branch instructions are I format. Jump or unconditional branch instructions are J format. Now I will be telling you about R format, and I and J format you will learn eventually. R type. R instructions are used when all the data values used by the instruction are located in registers. All R type instructions have the following format: operation code OP, first source register RS, second source register RT, destination register RD, and shift amount sham T, and opcode variant selector funct. You will learn about all of these eventually. Okay, first let me tell you about registers. Note that registers and memory are two different things. Registers are storage locations internal the processor. CPU instructions operate on these values directly, while memory is located external to CPU. Generally speaking, data has to be loaded into a CPU register from memory before the CPU can process it. Compiler associates variables with registers. So what about programs with lot of variables? Memory organization. Memory organization is one large array. The array contains bytes. In computer organization, people don't use the term index to refer to the array locations. Instead, we use the term address. Address and index mean the same. Each address stores one element of the memory array. Each element is typically 1 byte. There are some memory configurations where each address stores something besides a byte. For example, you might store a nibble or a bit. Bytes are nice, but most data items need something larger space. So here we have larger words. Words are just simply a 32-bit space or 4 bytes. There are 2 power 32 bytes with byte addresses from 0 to 2 power 32 minus 1, and 2 power 30 words with byte addresses 0, 4, 8, some like that to 2 power 32 minus 4. Words are aligned, that is, each has an address that is a multiple of 4. All addresses are like 4, 8, 12, 16, 20. It turns out there are two ways to store this in memory: big endian and little endian. Big endian is generally used in IBM mainframe Spark. Here, you store the most significant byte in the smallest address. It would look like how it is shown in the table, where zeroth address has the least significant one and the last address has the highest significant value 7. And little endian, it is generally used in Intel and AMD processors. They store the least significant byte in the smallest address, and it would look like how it is shown in the table below. Every MIPS program has two sections. There are dot data section and dot text section. The dot data section holds all the variables and data. So we initialize with dot data. This code just begins a data declaration section. In the second line we are typing message semicolon space dot scz and space and hello world in quotations. This dot scz just it tells the system the data type, and we use for texts we use dot scz. And now to create the function we go for dot text. Here we give all the instructions. So to initialize it we type dot text, and in the next line we say main to tell it that we are going to tell the main instructions. And the next line we say li space $v0, 4. It's a system call code for printing string equal to 4. There is load immediate. Think of it as a signal, just signal to the system. And next line we tell la space $a0, message. This is to load address of the string to be printed into $a0. $a0 is a register, as we talked already, and message is the one we already gave the data, and LA means just load address. So next we say syscall in the next sentence. That it's just a call operating system to perform operation in $v0. So next we give space so that syscall takes its argument from $a0. Next we say li space $v0, 10. Now this is system call code for terminating the execution. The syscall to call its argument.
Program termination. Unlike the higher level languages that we learned earlier like Python or Java, MIPS assembly does not include any instruction or block syntax to terminate the program execution. MIPS In MIPS, basically to terminate a particular program, we write a simple two-line syntax, that is li $v0, 10 and syscall. That's it. Without writing these two lines of code, the program will not be terminated, and it will look for further memory addresses to be continued further for their execution. MIPS arithmetic instructions. So all arithmetic and logic instructions have basically three operands, and the operand order in which the operands occur is fixed, having the destination first. So the operand code is given first, after that is given the destination, after that the left top, and then the right top. A simple example of this would be in consideration by taking the C code, basic C code, A is equal to B plus C. So we write this in MIPS as add, which is the OP code, and $S0. This is the destination where the variables are, where the final variable is saved. $S2 and $S3. These two variables are the variables on which the OP code or the operation is performed, and it is stored in S0. The typical example of this would be another C code example, like A is equal to B plus C plus D. Over here we have three variables on the right hand side. So for the MIP pseudocode for this would be add, which is the OP code, $S0 where the variable is saved, the destination, $S1 and S2 on which the operation is performed, and the second line what we do is we again write add, the OP code, and $S0 is the destination, and we add, since the previous instruction was saved in $s0 variable. So we add s3 to the existing $s0 variable and again store it in $s0. This is how basic MIPS code works. MIPS logical instructions. So let's go through a few examples of basic MIPS logical instructions that we commonly use while writing MIPS code. Basic instruction is AND, bitwise AND operator, as we all know, and I, where we use a constant instead of a variable, or a bitwise OR operator, or I, where we use a constant instead of a variable, NOR, a bitwise NOR operator, and SLL. This is a special logical instruction where we store the constant with a logical shift to the left side, and SRL is logical shift right.
SLT. SLT stands for set less than, and it is used for to set values. Suppose if $S0 is less than $S1, then it will set value of $T0 to 1, else 0. Similarly, for integer value, we will use SLTI. BNE. It stands for branch not equal, and it helps to jump to the given branch if two registers are not equal. And branch and BEQ stands for branch equal to, and it helps to jump to branch if two registers are equal. Similarly, BLE stands for branch less than, and it will jump to the given branch if two registers are less or equal to each other. And the last one is BGE. It stands for branch greater than. It will jump to given branch if two registers are greater or equal to each other.
So let's come to unconditional branch instructions. MIPS conditional branch instructions. It has J label, B label, $RA. These are useful for building loops and conditional control structures.
Let's do some example. Suppose you have to write MIPS code for this question. If I equals to j, then h equals to I plus j. In this case, we will use branch equal to. We have take $S0 to I, $S1 to j, and $S3 to h. In this, we are using branch equal to. If S0 and S1 are equal to each other, then it will automatically jump to branch do if, and it will add S0 and S1, and it will store the value of S1 and S0 to S3. And if S0 and S1 are not equal, then it will go to the next branch B, and it will jump to branch skip. Second example, if I is less than j, then we have to increase the value of I, else we have to increase the value of j. So we will use branch less than or equal to. We have take S3 is equals to I and S4 equals to j. Now we are using branch less than. If S3 is less than S4, then it will jump to the branch do, and it will increase the value of I, means S3. We will use add I. Or if branch S3 is greater than or branch S4, then it will not jump to branch 2, then it will go to next branch B, and it will jump to branch else, and in this branch it will increase the value of S4, means j, and after that it will jump to branch and if.
So let's look at the table in which we have service and code value in $V0. In print integer, we have to take value as 1. In print float, we have to take value as 2. In print double, we have to take 3. For printing statements, we have to take, like for string, we have to take 4. For read integer, we have to take 5. And read float is 6. And for read double, we have to take 7. And for read string, we have to take 8. And to exit or termination execution, we have to take $V0 as 10. And to print any character, we have to take value as 11. And to read a character, we have to take value as 12. Taking input from user. In this code, if we see the bold part, we have like $V0, comma 5. If you recall table, we can see that to store any integer, we have to take 5 in $V0. And syscall is for taking input from the users, and then we have to move it to a temporary storage.